a planet shaped like a lemon, an atmosphere full of carbon and helium, a year that ends in under 8 hours, and scientists say they cannot explain any of it. Webb just stared at a world orbiting a dead star, 750 light-years away. What it found broke every model we had. A lemon-shaped world squeezed by forces we barely understand, wrapped in chemistry that should not exist. We'll see a planet stretched by gravity, clouds made of soot, and an atmosphere with no oxygen, no nitrogen, nowhere to hide. If you enjoy the ride, like and subscribe. It keeps this going. Now, let's begin. 750 light-years away, there is a planet that breaks every rule we have. It orbits a dead star. It completes a full year in under 8 hours. Its sky has no oxygen, no nitrogen, and no water. And its shape, scientists describe it as a lemon. A giant, squeezed, stretched lemon drifting through one of the most violent environments in the known universe. When the James Webb Space Telescope pointed at this world in 2025, the team expected something unusual. They had already known about the planet since 2017. They knew the orbit was tight. They knew the host star was extreme. But they expected the atmosphere to at least follow some kind of pattern, something recognizable, something they had seen before on other worlds. The spectrum came back. The scientists looked at it, and the room went quiet. The atmosphere showed helium. It showed molecular carbon. It showed almost nothing else. No water, no methane, no carbon dioxide, no hydrogen in the amounts you would expect. The molecules that show up on nearly every other planet ever studied were simply gone. One researcher described the composition as something they could not fit into any existing model. The official NASA summary used the phrase, "defies explanation." That is not the language scientists reach for lightly. When a space agency publishes something and calls it impossible to explain, it means every framework they have tried has failed. Here is why that matters for you right now. Every planet we have ever found across thousands of discoveries falls into some kind of category. Hot Jupiters, mini Neptunes, rocky super-Earths. Each category comes with a set of rules. Rules about what the atmosphere should contain. Rules about how the orbit should look. Rules built from decades of data. This world, officially called PSRJ 232222650b, fits into 0 categories. Scientists are not arguing about which box to put it in. They are staring at a planet that seems to have arrived from outside the entire filing system. And here is the part that makes it stranger. Before Webb looked at the atmosphere, the planet was already considered one of the oddest objects in the known galaxy. The orbit alone was enough to baffle researchers. The host star alone was enough to make any astronomer stop and stare. The shape of the world itself, physically distorted by gravity, already had no clean explanation. Webb did not find a weird planet. Webb found a planet that was already weird and then made it weirder. That is the story we are following. Chapter by chapter, you are going to see every layer of this mystery pulled apart. The dead star it orbits, the gravity that squeezed it into a lemon, the atmosphere full of chemistry that should not survive at these temperatures. The clouds that look more like soot than anything you would find in a textbook, the winds that blow the wrong direction, the theories scientists are throwing at it, none of which fully stick. Each answer leads to a bigger question. Each layer of this planet turns out to be stranger than the one above it. By the time we reach the bottom, you will understand why astronomers are not just confused. They are rethinking the entire definition of what a planet is allowed to be. Right now, though, we need to go back to the beginning, before the atmosphere, before Webb, before 2017. We need to understand what kind of star this planet orbits, because the host star alone is one of the most extreme objects in the universe, and what happened to it, the death that created it, changed everything about the world that ended up circling its corpse. Long before any planet circled it, there was a star, a massive one, many times heavier than our Sunday. It burned bright and hot for millions of years, fusing hydrogen into helium, then helium into heavier elements, pushing outward with so much energy that its own gravity could barely hold it together. Then the fuel ran out. When a star that massive loses its fuel source, the core collapses. The collapse happens in less than a second. In that fraction of a second, the core crushes itself down to an object about 12 miles across. 12 miles. You could drive across it in 15 minutes on a highway, but that 12-mile ball contains more mass than our entire Sunday. The outer layers of the star, everything above the collapsing core, bounce off that dense ball and explode outward. That explosion is a supernova. It releases more energy in a few seconds than our sun will release in its entire 10 billion year life. What gets left behind is called a neutron star. A neutron star is so dense that a single teaspoon of its material would weigh about 1 billion tons on Earth. Picture filling a teaspoon from your kitchen with a piece of this object. That teaspoon would be heavier than a mountain, but the star at the center of our story is a specific kind of neutron star, a pulsar. And pulsars are even more extreme. A pulsar spins fast. Some spin hundreds of times per second. They fire narrow beams of radiation out from their poles as they rotate, and those beams sweep across space like lighthouse beams sweeping across an ocean. When Earth happens to be in the path of that beam, we detect a regular pulse. That pulse is where the name comes from. The pulsar in our story, called PSRJ 23222650, belongs to a class called millisecond pulsars. These are the fastest spinning ones. They did not start life spinning this quickly. They got spun up over time by pulling material from a companion object, a process that acts like a hand pushing a spinning top faster and faster over millions of years. Eventually, the companion was consumed or stripped away, and what remained was a pulsar rotating at an almost unimaginable rate. A millisecond pulsar also floods its surroundings with intense radiation, charged particles, X-rays, the kind of environment that strips molecules apart. The kind of environment that, by most standard thinking, should make it nearly impossible for a planet to hold onto an atmosphere at all. And yet, something is orbiting this pulsar. Something with a mass close to 3/4 of Jupiter. Something with an atmosphere that Webb was able to read. How did a planet end up there? How did it survive? How does it still have an atmosphere after being blasted by pulsar radiation for who knows how long? Scientists do not have clean answers yet. What they do have is data, a spectrum, a chemical fingerprint from a world that, by the rules of standard planet formation, should either not exist or should long ago have been stripped bare. The planet exists, the atmosphere exists, and neither one fits the story we thought we knew about how worlds form around dying stars. The next question is how we even found it, because the method scientists used in 2017 is one of the strangest detection techniques in astronomy, and it tells its own story. Finding a planet around a normal star is already hard. Finding one around a pulsar is a completely different kind of challenge. With a normal star, astronomers often watch for the star to dim slightly as a planet crosses in front of it. The planet blocks a tiny fraction of the starlight. Sensitive telescopes can measure that dimming and use it to calculate the planet's size, orbit, and rough location. That method does not work well with pulsars. Pulsars do not shine with visible light the way normal stars do. They pulse with radiation, and that is exactly what scientists used. The technique is called pulsar timing. Here is how it works. A pulsar fires its radiation beam with extraordinary precision. Millisecond pulsars are so regular in their timing that they rival atomic clocks for accuracy. Scientists measure when each pulse arrives at Earth and build up a very precise schedule. When nothing is disturbing the pulsar, the pulses arrive exactly when expected, over and over, like a perfectly timed heartbeat. But if something is orbiting the pulsar, That object's gravity tugs the pulsar slightly in different directions as it moves around its orbit. When the pulsar gets tugged toward Earth, its pulses arrive a tiny bit earlier than expected. When it gets tugged away, the pulses arrive a tiny bit late. The shift is small. We are talking about millionths of a second. But a millisecond pulsar is precise enough that even those microscopic shifts show up clearly in the data. Scientists used this method in 2017 to confirm that something with a mass close to 3/4 of Jupiter was orbiting PSRJ 23222650. They could calculate the orbit period, the distance, and the rough mass, all from watching the timing of radio pulses. The planet itself was invisible. Scientists never saw it directly. They inferred its existence from the way it pushed and pulled its own star. That detection alone was remarkable. Pulsar planets are extraordinarily rare. In the entire catalogue of confirmed exoplanets, only a handful orbit pulsars. The first exoplanets ever confirmed, back in the early 1990s, actually orbited a pulsar. At the time, scientists were stunned. A planet around a dead, radiating star seemed almost contradictory. And yet here was another one, a Jupiter-mass world circling a millisecond pulsar, detected through the ghost-like signature of timing shifts in pulses arriving from 750 light-years away. When the 2017 team published their findings, they flagged it as unusual but stopped short of calling it impossible. They knew the orbit was tight. They knew the environment was hostile, but without an atmosphere measurement, they could only guess at how strange this world truly was. That guess would have to wait 8 years. Webb changed everything in 2025, when it pointed its infrared instruments at the system and did something pulsar timing cannot do. It looked at the light filtering through the planet's atmosphere and read the chemical fingerprints hidden inside. What it found was a chemistry that no one had expected, a composition that no current model could explain, a spectrum that scientists described, in their own words, as defying explanation. But before we get to what Webb found in that atmosphere, we need to understand the orbit itself, because the planet's path around its dead star is so extreme that the orbit alone raises questions no one has fully answered. Imagine waking up on a planet where an entire year passes in under 8 hours. You go to sleep, you wake up. 365 days have already gone by on this world. PSR J23222650 B completes one full orbit around its host pulsar in just under 8 hours. Its orbital period is 0.32 days, which rounds out to roughly 7 hours and 45 minutes. That is the length of a full year on this planet. A school day on Earth lasts longer. To understand why the orbit is that fast, picture swinging something on a string. The shorter the string, the faster the object swings around. The longer the string, the slower. This planet is on an extremely short string. It sits only about 1 million miles from its host pulsar. 1 million miles sounds large until you compare it to our own solar system. Earth orbits the Sun at about 93 million miles. Mercury, the closest planet to the Sun, still sits about 36 million miles away. This planet sits at 1 million miles. It is 36 times closer to its host than Mercury is to the Sunday. At that distance, the pulsar's gravity is overwhelming. The planet does not drift slowly around a wide path. It hurtles. It races through its orbit at a speed that our own planet never approaches, completing its loop again and again and again, while Earth barely moves along its own path. Every day on Earth, this planet finishes approximately 3 full years. That speed creates a second problem beyond just the strangeness of a short year. At 1 million miles from a pulsar, the radiation environment is crushing. Pulsars fire intense beams of charged particles and high-energy radiation in all directions, not just along their poles. A planet sitting that close gets bathed in that radiation constantly. Every second of every orbit, the planet faces an energy bombardment that would strip the atmosphere from many worlds we know, and yet the atmosphere survived. Webb detected it. Read it. pulled chemical fingerprints from it. The atmosphere is thin compared to what you might expect, but it is there. That survival is itself a mystery scientists are still working through. One possibility is that the atmosphere is being constantly replenished, somehow, fed by material escaping from inside the planet. Another possibility is that the particular chemistry Webb found, dominated by helium and molecular carbon rather than hydrogen and oxygen, is somehow more resistant to pulsar radiation than a standard atmosphere would be. Neither explanation has been confirmed. What scientists do know, as a confirmed fact, is that the orbit places this world in a category of its own, an 8-hour year, a distance of 1 million miles, a speed and proximity that should, by many models, have ended this planet's atmospheric story long ago. The orbit is already extreme. The radiation is already extreme. The survival of the atmosphere is already a puzzle. But the orbit has one more consequence that is even more visual and strange. At 1 million miles, the pulsar's gravity does something to the planet itself. Something physical. Something you can almost picture. It squeezes it. Stand close enough to a powerful magnet, and you feel the pull. Stand even closer, and the pull gets stronger. Stand right next to it, and it yanks you in. Gravity works the same way, except it is not uniform across an object. The side of a planet facing a massive body feels a stronger pull than the far side. That difference in pull, from one side to the other, is called a tidal force. On Earth, tidal forces from the moon pull on our oceans and create the tides you see at a beach. On PSR J232222650b, the tidal forces are something else entirely. This planet sits 1 million miles from a neutron star. A neutron star with more mass than our Sun packed into a ball 12 miles wide. The gravity gradient from one side of this planet to the other is extreme. The near side gets pulled much harder than the far side. The result is that the planet gets physically stretched. Picture holding a ball of soft clay and pulling both ends in opposite directions. The ball would elongate. It would stretch into an oval shape. Something similar is happening to this world, except the force doing the stretching is pure gravity, and the planet is a ball of gas and compressed matter the size of Jupiter. Scientists describe the shape as lemon-like. The planet bulges outward at the points closest to and farthest from the pulsar, and flattens slightly at the sides. It is an egg shape, a squeezed sphere, a world deformed by the grip of its dead star. This kind of tidal distortion happens on other worlds in our solar system too, but at much smaller scales. Io, one of Jupiter's moons, gets squeezed by Jupiter's gravity, and that squeezing generates heat inside it, making Io the most volcanically active body in our solar system. Europa, another moon of Jupiter, gets enough tidal heating to keep a liquid ocean under its icy surface. For PSRJ 23222650b, the tidal forces are far more extreme. Scientists confirmed the lemon shape through Webb's data, and it raises a question that has no clean answer yet. If the planet is being stretched this powerfully, what is happening inside it? Tidal forces this strong generate heat deep inside the planet. That internal heat has to go somewhere. It likely drives circulation. It likely powers whatever climate and wind system this planet has. And it may be contributing to the bizarre atmospheric chemistry Webb detected by cooking material up from the interior and pushing it into the air. The shape is striking on its own, a lemon-shaped world, squeezed and distorted, racing around a dead star at 1 million miles per hour. But the shape is also a symptom of something deeper. The same forces that sculpted the outside of this planet are also working on the inside, heating it, stirring it, and possibly producing the conditions that created an atmosphere unlike anything in our catalogue. Now here is the next layer of strangeness. All of that, the orbit, the shape, the tidal forces, was known before Webb. Scientists could describe the orbit, estimate the size, and infer the distortion. What they could not see was the temperature. And when they started trying to measure it, they discovered a problem. Most measurements in astronomy have a clean answer. The planet is this far away. The orbit takes this long. The mass is approximately this much. You run the numbers. You check the data. You publish. Temperature on PSRJ 2322-2650. B. Refuses to cooperate. Different research groups looking at different parts of the data have come back with different numbers, and the spread is wide enough to be its own mystery. Some estimates point to around 1900 degrees Kelvin, which is roughly 2900 degrees Fahrenheit. A Nature research highlight cited a different value, closer to 1300 degrees Kelvin, around 1900 degrees Fahrenheit. Some press summaries reported a range spanning from about 1200 degrees Fahrenheit at the low end to 3700 degrees Fahrenheit at the high end. That range is enormous. 3700 degrees Fahrenheit is hot enough to melt iron. 1200 degrees Fahrenheit is hot enough to glow orange-red. Those are very different conditions, and they produce very different chemistry. Part of the reason for the disagreement is that the planet likely has no single uniform temperature. At 1 million miles from a pulsar, with an orbit that takes under 8 hours and tidal forces actively reshaping the planet, the day-side and night-side conditions are probably very different. The side facing the pulsar absorbs radiation. The side turned away is colder. When researchers measure the planet's average temperature, they may be catching different parts of the planet at different moments, which produces different numbers depending on what they measure and when. Webb's data added new detail to this picture. The dayside shows specific chemical signatures in the atmosphere, dominated by molecular carbon. The night side shows something completely different, a thick, grey cloud or dust layer that blocks most of the signal. Those two sides behave differently, and treating the planet as one single temperature is probably too simple. Researchers have flagged the temperature range as unresolved. Scientists have not published a single confirmed global temperature for this world. That classification is important for understanding the atmosphere, because the temperature determines what molecules can survive, what breaks apart, and what forms. If scientists cannot pin down the temperature, it becomes harder to build a model that explains the chemistry. And the chemistry is already the biggest problem. Here is a number that puts the heat in context. The surface of our sun sits at about 10,000 degrees Fahrenheit. This planet, at its hottest estimates, sits at about 1/3 of that. Still hot enough to melt rock, still hot enough to vaporize water instantly, still hot enough that you would expect it to drive certain chemical reactions in the atmosphere. But the chemistry Webb found does not match what those temperatures should produce. The molecules present are wrong. The molecules absent are equally wrong, and that mismatch is what sent scientists back to their models with no clean answers. Before we get to the atmosphere itself, though, we need to stop for a moment and appreciate what Webb actually did, because detecting an atmosphere around a planet orbiting a pulsar is a technical achievement that should have been nearly impossible. Webb launched in December 2021. It traveled 1 million miles from Earth and settled into a stable orbit around a gravitational balance point called the second Lagrange point. From there, it points outward into the universe with a mirror nearly 21 feet wide, coated in gold, cooled to temperatures close to absolute zero. The reason Webb needs to be that cold is because it works in infrared light. Infrared is heat radiation. Every warm object gives it off. If the telescope itself were warm, its own heat would flood the instruments and drown out the signals from distant worlds. Webb keeps its instruments colder than any natural environment on Earth so that its own heat does not contaminate the science. When Webb looks at an exoplanet, it does not take a photograph. The planet is far too small and too faint, hidden next to the brilliant glare of its host star. Instead, Webb uses a technique called transmission spectroscopy. Here is how it works. As a planet passes in front of its host star, starlight filters through the edges of the planet's atmosphere. Different molecules in the atmosphere absorb different wavelengths of that light. Hydrogen absorbs some wavelengths. Water absorbs others. Carbon dioxide absorbs a different set entirely. Each molecule leaves its own unique mark on the light, like a fingerprint on glass. Webb captures that light, stretches it out into a spectrum, and reads the pattern of absorbed wavelengths. From that pattern, scientists can identify which molecules are present and in roughly what amounts. For PSR J23222650b, the challenge was that a pulsar is not a normal star. Pulsars do not put out the kind of steady, visible starlight that makes transmission spectroscopy straightforward. The team had to adapt their approach, using the planet's transit across the pulsar's radiation to pull the atmospheric signal out of extremely noisy data. They succeeded. The spectrum they got back was clear enough to identify specific molecules, and those molecules immediately raised flags. The fingerprints matched helium and molecular carbon, specifically forms called carbon-2 and carbon-3. Those are 2-atom and 3-atom chains of pure carbon. They show up in environments like the outer atmospheres of certain red giant stars, in comets, in interstellar clouds. Seeing them as the dominant feature of a planet's atmosphere was, according to the team, completely unexpected. Webb's data also showed what was missing: no clean water signal, no methane, no carbon dioxide, no rich hydrogen signature. The standard atmosphere building blocks that show up across hot exoplanets were absent or nearly absent. That combination, what was there and what was gone, was what made the spectrum impossible to explain with current models. Scientists had their fingerprints, they had their data, and the data was pointing at something that should not be possible under any standard formation scenario. The helium alone is worth stopping on, because helium in an atmosphere is its own puzzle, and the next chapter is entirely about why. Helium is the second most common element in the universe. After hydrogen, it is everywhere. Stars fuse it. Gas giant planets are full of it. Even Earth has trace amounts drifting in the upper atmosphere, slowly leaking out into space because our gravity is not strong enough to hold it. But helium does not normally dominate a planet's atmosphere the way it dominates this one. On Jupiter, our solar system's biggest gas giant, the atmosphere is mostly hydrogen. Helium makes up roughly a quarter of it. On Saturn, same story. Hydrogen first, helium second. That pattern makes sense because hydrogen and helium formed together in the early universe, and both accumulated in large quantities when giant planets grew from the gas in their forming solar system. On PSR J23222650b, hydrogen appears to be mostly gone. Helium is the main ingredient. That flip is strange, and it tells scientists something important. Hydrogen is lighter than helium. It escapes from an atmosphere more easily. At extreme temperatures and under intense radiation, hydrogen atoms move fast enough to exceed the escape velocity of the planet, meaning gravity cannot hold them, and they drift off into space. This process is called atmospheric escape, and it happens slowly on most worlds, but can happen rapidly on worlds sitting very close to intense energy sources. PSR J23222650b sits 1 million miles from a pulsar that blasts radiation in all directions. Over time, hydrogen, being the lightest element and the easiest to strip away, could have been lost to space. What gets left behind when hydrogen escapes is the heavier stuff, including helium, including carbon. That is one possible explanation for the helium-dominated sky. The planet may have started with a normal mix of hydrogen and helium, but the pulsar's radiation gradually stripped the hydrogen away, leaving a helium-rich remainder. The problem with that theory is that it does not explain the molecular carbon. If the atmosphere were simply a hydrogen-depleted version of a normal gas giant atmosphere, you would expect to see more of certain other molecules. Instead, the carbon shows up in an unusual molecular form that goes beyond what hydrogen loss alone would explain. Helium atmospheres have been detected on other exoplanets before. A few hot Jupiters orbiting very close to normal stars show helium escaping from the upper atmosphere in streams. But those detections involve helium drifting away, leaking out. On this world, helium is the dominant ingredient, staying put, and the chemistry around it is something different entirely. Scientists marked this as a confirmed observation. The helium dominance is real. The explanation for it remains a theory, and not a fully satisfying one. The bigger puzzle, the one that gets scientists genuinely stuck, is the carbon that sits alongside the helium. Because the form of carbon in this atmosphere is something that belongs more in space clouds and comets than in a planetary sky. Carbon is everywhere in the universe. It is inside you. It is in the air you breathe, bonded with oxygen as carbon dioxide. It is in wood, in plastic, in every living thing. Carbon bonds with almost everything, and that bonding tendency is part of what makes it so essential to chemistry. But the carbon web found in this planet's atmosphere was different. It was not bonded with oxygen to form carbon dioxide. It was not bonded with hydrogen to form methane. It was pure carbon, bonded only to itself in chains of 2 and 3 atoms. 2 carbon atoms bonded together form a molecule called carbon-2, written as C2. 3 carbon atoms bonded together form carbon-3, written as C3. These molecules are known to science. They show up in the outer layers of dying red giant stars, where temperatures are high and other elements are scarce. They appear in the glowing tails of comets, where sunlight breaks apart larger molecules and leaves carbon chains floating free. They exist in the cold gas clouds between stars. They have never been the dominant feature of a planet's atmosphere, until now. At the temperatures on PSR J 2322650b, carbon chemistry is complicated. When carbon, oxygen, and hydrogen are all present together, they tend to combine into molecules like carbon monoxide, carbon dioxide, and methane. The element rarely stays as bare carbon chains at temperatures this high, because it has so many opportunities to bond with other atoms. For carbon-2 and carbon-3 to dominate the spectrum, the atmosphere would need to be nearly free of oxygen and hydrogen, and that is exactly what Webb found. The oxygen and nitrogen signals are absent or nearly absent. The atmosphere appears stripped of the 2 elements that would normally grab the carbon and turn it into something more familiar. Carbon-2 and carbon-3 filling the sky of a giant planet is, according to researchers, unlike anything in the existing catalogue of exoplanet observations. A team member described the spectrum as something that does not match any known atmospheric model for a planet of this type. And here is the part that makes scientists uncomfortable. At the temperatures this planet likely experiences, bare carbon chains should be unstable over long time periods. They should combine with something. They should react. They should become something else. The fact that they dominate the atmosphere suggests either a constant process of replenishment or conditions so unusual that the normal rules of molecular chemistry do not apply here the way they would elsewhere. No confirmed explanation exists yet for why the carbon is in this form. Multiple teams are working on models. None have published a fully consistent picture. What makes this chapter of the story even stranger is that the carbon in the atmosphere is just the surface of a much deeper problem. Because to understand why the carbon exists this way, you have to ask where the oxygen went. And that question leads somewhere even more unsettling. Oxygen is one of the most common elements in the universe. In most gas giant atmospheres, it bonds with carbon and hydrogen to produce water, carbon dioxide, and other familiar molecules. Even on the most extreme hot Jupiters, water vapor shows up in the spectrum. It is almost a background assumption in atmospheric science. Find a planet, find some oxygen signal. On PSRJ 23222650b, the oxygen signal is gone. Webb's spectrum showed an atmosphere dominated by helium and molecular carbon, with no clear sign of the oxygen-bearing molecules that standard models predict. Oxygen appears depleted to a level that researchers describe as outside normal expectations for a planet of this mass and temperature range. Where did it go? One theory is that oxygen was stripped away along with hydrogen over a long period of pulsar radiation bombardment. Lighter molecules escape more easily, and water, which contains both hydrogen and oxygen, could have been lost in large quantities over millions or billions of years. A second idea is that the oxygen was never there in the same amounts to begin with, that this world formed in an oxygen-poor environment or in some unusual way that gave it a non-standard chemical inventory from the start. A third possibility is that the oxygen is present but bound up in solid compounds deep inside the planet, locked away where Webb's infrared instruments cannot detect it. In that case, the atmosphere might be stripped of oxygen, while the interior still holds large quantities of it in a different form. None of these ideas has been confirmed. Scientists listed the missing oxygen as one of the core unexplained features of the planet. The missing nitrogen adds another layer to the puzzle. Nitrogen is the main ingredient in Earth's atmosphere and shows up in many planetary systems. On PSRJ 2322-2650b, nitrogen also appears depleted. Two common, abundant, reactive elements, both absent. Their absence is as informative as what is present. When two things are missing together, it suggests a single cause rather than two separate coincidences. Something stripped this atmosphere, or built it, in a way that left helium and carbon behind while removing or sequestering everything else. The honest answer from the scientific team is that they do not know what that something is. The observation is confirmed. The explanation is a collection of competing theories, and here is why the missing oxygen and nitrogen matter beyond just this one planet. If a world can exist with an atmosphere this different from anything we have modeled, then our atmosphere database, our catalogue of what is possible, is incomplete. There may be other worlds out there with exotic chemistry we have never thought to look for, because our models told us such chemistry could not survive. This planet is telling us our models have gaps. The night side of this world has its own secret. While scientists struggled to explain the day side chemistry, Webb's data revealed a completely different problem hiding in the planet's shadow. When Webb observed this planet, it did not just collect data from the day side. Astronomers tracked the planet through part of its orbit and gathered light from the night side as well. The night side spectrum looked completely different from the day side. Where the day side showed chemical fingerprints, molecular carbon signatures, helium signals, complex absorption patterns, the night side showed something that blocked most of those features. A thick layer, dense, grey, sitting in the upper atmosphere like a lid. Scientists describe it as a thick grey dust or cloud deck. On other exoplanets, cloud decks are common. Many hot Jupiters have silicate clouds, made from vaporized rock minerals that condense in the cooler upper atmosphere. Some worlds have iron clouds, where iron metal vaporizes on the hot day side and condenses into droplets on the cooler night side. On PSR J23222650b, the cloud composition is strange. Given the carbon-rich atmosphere and the near absence of oxygen-bearing minerals, the cloud deck is unlikely to be silicate or iron in the usual form. Researchers have described the particles as possibly soot-like carbon particles, dark grains condensing out of a carbon-rich sky. Picture a sky where it rains charcoal. On the night side of this planet, the temperature drops compared to the day side. Carbon molecules that are floating as gas on the hot day side may condense into solid particles when they drift into the cooler dark. Those particles cloud the sky, block the signal Webb is trying to read, and settle in thick, grey layers. A sky of carbon soot blocking the view from outside. A chemistry below that nobody can explain. A day side glowing with molecular fingerprints that belong in a comet tail. Webb's data captured day side and night side as two completely different environments on the same world. The contrast between them is extreme, and that contrast is itself a clue. Extreme day-to-night temperature differences drive powerful winds, and on this planet, those winds are measurable. But here is what makes the cloud story even more striking. If the clouds are made of soot-like carbon particles, those particles are raining down into the lower atmosphere. And in the lower atmosphere, where pressure increases sharply, carbon under pressure behaves differently than carbon in an open sky. Under high pressure and high temperature, carbon can form something else entirely. something valuable, something that, on Earth, takes millions of years to produce under miles of rock. Scientists have raised the possibility that inside PSR J232222650b, conditions might be right for diamond formation. That idea is not confirmed, but it is based on real atmospheric chemistry, and the next chapter is where that theory goes. Diamonds form under pressure, extreme pressure. On Earth, they start as carbon deep underground, roughly 100 miles below the surface, where rock presses in from every direction. That pressure squeezes the carbon atoms into a tight, ordered structure. Over millions of years, the result is a diamond crystal. Other worlds in our solar system may already do something similar. Models of Neptune and Uranus suggest that carbon in their interiors, under the extreme pressures of those giant planets' depths, could compress into diamond crystals that then rain down toward the core. Scientists call this diamond rain, and some experiments in labs have produced conditions that seem to support the idea. PSRJ 23222650b is a different beast. Its atmosphere is saturated with carbon. Its dayside temperatures are high, but pressure increases rapidly with depth inside a gas giant, and at sufficient depth, even very high temperatures cannot stop pressure from forcing carbon into solid forms. Researchers who looked at this planet's unusual chemistry raised the possibility that diamond formation might be happening inside this world. The carbon-rich atmosphere feeds into the interior. Pressure builds with depth. The conditions in the deep interior might reach the range where carbon crystallizes. Diamond rain falling toward the core. That idea is striking, but scientists were careful to label it as a hypothesis. Webb observed the atmosphere. Webb cannot see through the planet. What is happening in the deep interior of PSRJ 23222650b is beyond the reach of any current instrument. The diamond rain theory is based on analogy with Neptune and Uranus, combined with the unusually high carbon content of this planet's atmosphere. On Neptune and Uranus, the carbon content is much lower, yet models suggest diamond formation may still occur. On a world where carbon dominates the sky, the argument runs, diamond formation could be even more likely or more intense. Here is a number that helps picture the scale. The pressure at the center of Jupiter, the biggest planet in our solar system, is around 45 million times the pressure at Earth's surface. At that pressure, carbon does not stay as gas or even as soft material. The structure of the atoms themselves gets forced into tight geometric patterns. Diamond is the result. If PSRJ 23222650b has a similar internal structure, and if the carbon raining down from the clouds reaches sufficient depth, then somewhere below the clouds and below the gas layers, there may be a region of diamond formation actively happening right now. A planet making diamonds while orbiting a dead star under a soot-colored sky, on a year that lasts less than 8 hours. That is a theory, but the winds above it are confirmed. And confirmed winds tell their own story about what drives the climate of this extreme world. Weather on Earth is driven by one main engine. The sun heats the equator more than the poles. Warm air rises, cool air sinks, and winds move heat from where there is too much to where there is too little. That difference, equator versus poles, warm versus cool, drives everything from gentle breezes to hurricanes. On PSRJ 23222650b, the main driver of weather is not latitude. It is the difference between day and night. With an orbit of under 8 hours and a likely tidal log, where one side of the planet permanently faces the pulsar and the other side permanently faces away, the temperature difference between dayside and nightside is extreme. The dayside absorbs radiation constantly. The nightside sits in perpetual dark. That contrast creates an enormous pressure difference, and pressure differences drive wind. Scientists reported strong westward winds on this planet. That direction matters. On tidally locked planets with hot daysides and cold nightsides, many models predict that the hottest point would be shifted slightly eastward from the directly lit point, because eastward winds carry heat around the planet. Westward winds suggest the opposite pattern is dominating the circulation. Westward circulation has been observed on a few other exoplanets. It typically implies a specific kind of atmospheric flow where the upper and lower layers of the atmosphere move in opposite directions, or where the planet's rotation and its orbit interact in unusual ways. On PSRJ 2322-2650b, with its already unusual chemistry and its lemon-like shape affecting atmospheric dynamics, the wind direction adds another data point that does not fit neatly into standard models. Strong westward winds also carry heat from the day side into the night side differently than eastward winds would. They affect where clouds form, how thick they get, and what chemical reactions happen at different points around the planet. The soot-like cloud deck on the night side is likely shaped in part by these wind patterns. Carbon particles from the dayside chemistry get carried westward and condense in the cold of the night side. The wind data comes from the way spectral lines shift slightly depending on which part of the atmosphere is moving toward or away from Webb's instruments. Even from 750 light-years away, the Doppler shift of those molecular signatures is measurable. The shift told scientists the wind direction. That is extraordinary. A telescope measures the wind direction on a world 750 light-years away, a world orbiting a dead star, a world with a carbon sky and a lemon shape, and reports the winds blow west. Every measurement Webb pulls from this planet adds detail to a picture that grows stranger with each addition. The winds are real, the clouds are real, the carbon chemistry is real, the helium dominance is real, and the sum of all those real, confirmed facts is a planet that no existing formation model can fully explain. A team of scientists stared at this data and came to one conclusion. We do not know how this world formed. That question, how and where and when this planet was born, is where the story goes next. And the answer is still deeply unsettled. When a star forms, it pulls in gas and dust from the cloud around it. The leftover material that does not fall into the star forms a flat, spinning disk. Over millions of years, material in that disk clumps together. Small clumps attract larger ones. Larger ones become planetesimals. Planetesimals collide and merge. Eventually, planets form. That is the standard story. The core accretion model. It is supported by observations across hundreds of planetary systems and has held up well for decades. PSRJ 2322-2650b does not fit that story cleanly. The problem is the host star. The pulsar at the center of this system was once a massive star. When that star died, it exploded as a supernova. Supernovae are violent events. They send shockwaves outward at a significant fraction of the speed of light. They vaporize nearby material. They strip away any disk that was forming around the star. If the planet formed before the supernova in a disk around the original massive star, how did it survive the explosion? At 1 million miles from the host, it would have been inside the star's outer layers when the supernova happened. It could not have stayed there and survived intact. If the planet formed after the supernova, from material that fell back onto the neutron star, or from debris left by the explosion, then it formed in an extremely unusual way, from material already processed by a stellar death in a radiation-soaked environment, with no normal disk to work from. Neither scenario has a clean, confirmed formation pathway. Scientists have proposed a third idea. Maybe the planet formed in the original disk, before the supernova, but much farther out from the star. The explosion then kicked it into a new, tighter orbit. Orbital mechanics after a supernova are chaotic. A surviving companion object could, in theory, end up in a completely different orbit than the one it started in. Each of those possibilities carries its own set of problems that researchers have not resolved, and there is a fourth option, one that scientists raised but have not confirmed, that this object was never a planet in the traditional sense at all. That idea, that this world might be something other than a planet, is strange enough to deserve its own chapter. Because if it is true, it changes what this object is and how we should think about everything Webb found in its atmosphere. Planets form from disks. They accumulate gas, rock, and ice. They grow slowly over millions of years in the cold material orbiting a young star. That is the standard definition. That is what a planet is. But there is another way to produce a Jupiter mass object. You start with a star. Stars come in a range of sizes. The smallest true stars, called red dwarfs, are still much more massive than Jupiter. But there is a class of objects between large planets and small stars called brown dwarfs. Brown dwarfs are too small to sustain hydrogen fusion the way true stars do, but they are far more massive than gas giants. Below brown dwarfs, there is a grey zone, objects that blur the line between a very massive planet and a failed stellar remnant. Some researchers raise the possibility that PSR J232222650b might be the remnant of a companion star, rather than a planet that formed in a disk. Here is the scenario. The original massive star that became the pulsar may have had a binary companion, a second star orbiting alongside it. When the massive star expanded into a red giant before exploding, it could have begun stripping mass from the companion. Over a long period, the companion lost most of its material to the primary star. The primary used that stolen material to spin up into a millisecond pulsar. The stripped companion was left as a small, dense remnant with far less mass than it started with. Under this theory, PSR J232222650b is not a planet formed from a disk. It is the shrunken leftover of a second star that was slowly consumed by the pulsar's predecessor. The atmosphere that Webb detected would then be the remnant of that companion's outer layers, transformed and depleted over billions of years of mass loss. This would explain some things. A stellar remnant might have unusual chemical abundances. A stripped star loses its outer hydrogen-rich layers first, which could explain why hydrogen is depleted. The carbon and helium that remain could be from deeper layers of the companion star's original structure. The theory does not explain everything. It does not fully account for the molecular carbon forms Webb detected, and the oxygen depletion still needs work under this model. Scientists are honest about the fact that neither the planet formation story nor the stellar remnant story fully accounts for what Webb found. Both remain possibilities. Both have gaps. What they agree on is that whatever this object is, it is real. It has a measurable atmosphere, and the atmosphere is unlike anything else in the current catalogue of characterized worlds. The stellar remnant idea forces a bigger question. If this object could be the transformed corpse of a former star, then the labels we use, planet, brown dwarf, stellar remnant, may be too rigid. The universe appears capable of producing objects that slide between categories. And if one such object exists, there are likely more. But all of that hinges on a number scientists cannot agree on. A number that determines how far away this system actually is, and why the disagreement matters more than it might seem. Science is supposed to give clean answers. A planet is this far away. Measure it, calculate it, publish it. For PSR J232222650b, the distance measurement is one of the rare cases where published sources disagree enough to matter. The 2017 discovery paper and related catalogue material calculated the distance using pulsar parallax, a technique that measures the tiny shift in the pulsar's apparent position as Earth moves around the Sunday. From that measurement, the team derived a distance of roughly 750 light-years. That is the value anchored in direct observational data from the discovery team. Several news articles and later summaries, including some published after Webb's 2025 observations, cite the distance as over 2,000 light-years. 750 light-years and 2,000 light-years are not close to the same number. 2,000 is nearly 3 times further. That difference changes the apparent brightness of the pulsar as seen from a distance, affects how researchers model the radiation environment around the planet, and influences estimates of the planet's temperature derived from the amount of radiation it receives. For a script, the safest approach is to use the parallax-based figure of about 750 light-years, since that comes from the most direct measurement in the reviewed source set, while noting that some later reports cite a larger value. The distance dispute is a reminder that even confirmed discoveries carry uncertainty at their edges. Astronomy is a science of inference. We measure light, timing shifts, spectral patterns, and we build models. Most of the time, those models converge. Sometimes, they do not, and the disagreement itself becomes a data point. For PSRJ 2322-2650b, the uncertainty in distance layers onto a stack of other uncertainties: temperature, formation history, interior structure, cloud composition. The planet is real. The atmosphere is real. The uncertainty around almost every other detail is also real. What the distance debate highlights is a truth about this discovery. Webb has given scientists a clear atmospheric spectrum. That spectrum is precise enough to identify molecular carbon and confirm helium dominance. But precision in one measurement does not resolve questions that require different instruments, different methods, or different observations entirely. Every answer Webb provides opens 3 more questions. That is a pattern with this planet. And the biggest open question, the one that keeps researchers working through models at night, is whether any of this, the orbit, the atmosphere, the shape, even the chemistry, fits into a universe where we thought we understood where planets could and could not survive. Because the next chapter is about a question that sounds simple but leads somewhere unsettling. Can this planet actually survive long term? And if the answer is no, what does it mean that we are seeing it right now? Planets are supposed to last billions of years. They form slowly, settle into stable orbits, and hold on. Our solar system is 4.5 billion years old, and the planets look roughly the same today as they did long ago. Stable orbits, stable atmospheres, stable enough for life to develop on at least one of them. PSR J2322-2650b does not sit in a stable environment. Every second of every orbit, this planet receives intense radiation from the pulsar. High-energy particles slam into the upper atmosphere. Some of that energy drives atmospheric escape, stripping lighter molecules away and sending them drifting into space. The hydrogen loss that may already have occurred is one sign of this ongoing erosion. At 1 million miles from a pulsar, the intensity of radiation is orders of magnitude higher than anything the planets in our solar system experience. Mercury, the closest planet to our Sun, receives about 10 times more radiation than Earth does. This planet sits 36 times closer to its host than Mercury sits to the Sunday. The radiation environment is extreme by comparison, even to Mercury. The tidal forces add a second stress. As the planet orbits, the pulsar's gravity flexes and stretches the planet rhythmically. Every orbit, the planet is squeezed from slightly different angles as it moves. That flexing generates heat inside the planet, similar to how squeezing a rubber ball generates warmth. Over geological time, tidal flexing can alter the internal structure of a planet and drive material from the interior toward the surface and atmosphere. The combination of atmospheric stripping from above and tidal heating from below creates a system that is actively changing. The planet today is likely different from the planet as it was 1 billion years ago. The atmosphere may be thinner, the chemical composition may have shifted, the lemon shape may have become more pronounced as the orbit has evolved. How long the planet can maintain any atmosphere at all is unknown. Some models suggest that planets this close to millisecond pulsars lose their atmospheres relatively quickly on cosmic timescales, meaning millions rather than billions of years. Others suggest that certain atmospheric compositions are more resistant to radiation stripping and can persist longer. The specific chemistry Webb found, dominated by helium and molecular carbon, is unusual enough that no model has been built yet that predicts exactly how long it will last. The fact that the atmosphere exists at all may mean one of two things. Either this planet formed recently enough that the atmosphere has not yet been stripped away, or the atmosphere is being actively replenished from inside the planet fast enough to keep pace with the loss. Neither option is confirmed. What scientists do know is that they caught this world at a specific moment, an atmosphere that should not be there, on a planet that should not have survived, around a star that should have destroyed everything nearby when it died. Every piece of this system seems to be defying the expected timeline, and catching it now raises a question that connects this bizarre world back to something much larger. If planets can survive in environments this extreme, if atmospheres can persist around pulsars, if chemistry this unusual can exist, then how many other impossible-seeming worlds are out there that we simply have not looked at yet? That question is where the story goes next. Astronomers have confirmed over 5,500 exoplanets. That number sounds large. It is actually a tiny sample. Our galaxy contains somewhere between 200 billion and 400 billion stars. If even a fraction of those stars host planets, the total number of worlds in the Milky Way alone runs into the hundreds of billions. Some estimates put the average at more than one planet per star. 5,500 confirmed planets against hundreds of billions of possible ones means we have surveyed a fraction of what is out there. And the planets we have found are not a random sample. They are a biased one. Every detection method we use favors certain kinds of planets. Transit detection, watching for a star to dim as a planet crosses in front of it, works best for large planets in tight orbits around bright stars. Pulsar timing works only for planets around pulsars, which are rare. Direct imaging works only for large planets far from their stars. Each method has a blind spot, and those blind spots add up. What that means is that the catalogue of 5,500 worlds reflects what our tools can see, not what actually exists. Entire categories of planets may be common in the galaxy and completely absent from our list, simply because no current telescope can find them efficiently. PSR J 232.22650b represents one of those blind spots made visible. Pulsar planets are so hard to detect and so unexpected that most surveys do not prioritize looking for them. The discovery in 2017 happened because a team was doing careful pulsar timing work and noticed the timing anomaly. If they had been focused on something else, the planet would still be unknown. How many other pulsar planets are orbiting dead stars right now, undetected, with exotic atmospheres that our models cannot explain? Scientists do not know. The honest answer is that pulsar planet surveys have been limited, and the sample size is too small to draw conclusions about how common or rare these systems are. The same logic applies beyond pulsar planets. If an atmosphere dominated by molecular carbon can exist on one world, what other chemical combinations are out there that we have not thought to look for? Our atmospheric models are built from the worlds we have seen. This planet suggests those models may be missing entire branches of chemistry. Webb is beginning to expand the census. Its infrared sensitivity allows it to characterize atmospheres that earlier telescopes could not read. Each new atmospheric spectrum it collects adds a data point to a map that is still mostly blank. PSR J 232.22650b is one of the first entries in a section of that map we did not know existed. A section labeled Planets Around Dead Stars with Carbon Skies in orbits shorter than a workday, shaped by forces that should have destroyed them. That section may be rarer than anything else in the catalogue, or it may turn out to be a whole neighborhood of planets we simply have not visited yet. Either answer changes how we think about the limits of planetary survival, and understanding those limits matters far beyond pure astronomy, because it connects directly to one of the biggest questions science has ever asked. For most of the history of astronomy, the question of where life could exist came with a simple answer. Look for a planet in the habitable zone around a sun-like star. The habitable zone is the range of orbital distances where liquid water can exist on a rocky surface. Too close, and water boils. Too far, and it freezes. In the middle, you get a world that could, in principle, support life. That definition made sense as a starting point. It was built on what we knew. Liquid water is essential to every form of life found on Earth. Sun-like stars are the ones we understand best. Rocky planets in the right orbital zone seemed like the most natural place to look. PSRJ 23222650b forces that definition to stretch. The planet itself is almost certainly not habitable by Earth standards. It orbits a pulsar, receives crushing radiation, has an atmosphere with no oxygen, no water, and no nitrogen, completes a year in under 8 hours, and gets physically squeezed into a lemon shape by tidal forces. Nothing about it fits any definition of a place where Earth-like life could exist, but survivability is a broader concept than habitability. The question this planet asks is not whether life could live there. The question is whether complexity can survive there at all, whether chemistry can persist, whether structure can hold together in environments we once assumed were purely destructive. The answer Webb provided is yes. Complex molecular chemistry, in the form of carbon-2 and carbon-3, survives in this atmosphere. A structured cloud deck persists on the night side. Organized wind patterns circle the planet. The system has internal dynamics, circulation, and chemical processes that are ongoing and active. None of those things should have been able to persist, by older assumptions, in an environment this hostile. That changes the boundary of what astronomers call survivable conditions. On Earth, biologists have found life in places once considered completely inhospitable. Bacteria in boiling hot springs, organisms in Antarctic ice, microbes living in solid rock miles underground. Each discovery pushed the boundary of what life can tolerate. The discovery of PSRJ 2322222650b's atmosphere pushes a parallel boundary. Chemistry can survive closer to a pulsar than we thought. Atmospheres can persist in radiation environments we once considered lethal to any organized molecular structure. That does not mean life is there. There is zero evidence of biology on this world. What it means is that the set of environments we consider capable of hosting complex processes is larger than it was before Webb looked at this planet. And a larger set of survivable environments means a larger set of places worth investigating. The next question that follows naturally is what future telescopes might find if they look harder at worlds like this one. Webb is the most powerful space telescope ever launched. Its gold mirror, its infrared sensitivity, its position far from Earth's atmosphere. Everything about it was designed to push the boundary of what we can observe in the universe. And yet Webb cannot see through PSRJ 23222650b. It cannot directly image the planet's surface or interior. It cannot measure the planet's exact radius from independent observations. It cannot determine with certainty what is happening at depth inside the planet or how the atmosphere changes over time. Those limitations point to what the next generation of instruments would need to do. Several major telescope projects are in development or early construction. The extremely large telescope, being built in the Chilean desert, will have a primary mirror about 39 meters wide, nearly 3 times the width of Webb's golden mirror unfolded. That size gives it collecting power. Webb cannot match for certain kinds of observations. Radio telescope arrays are being expanded and improved globally. Pulsar timing with more sensitive arrays would allow scientists to measure the orbital dynamics of PSRJ 23222650b with greater precision, potentially revealing whether the orbit is stable or slowly changing, and whether the planet is gaining or losing mass over time. X-ray telescopes focused on the pulsar itself could measure exactly how much radiation the planet receives at different points in its orbit, giving researchers a more precise input for models of atmospheric stripping and survival. None of these future instruments will answer every question about this planet. Some answers require being there, or at least much closer than 750 light-years, but each new instrument fills in a piece of the picture that Webb could only outline. The atmospheric spectrum Webb collected in 2025 is a starting point. Researchers are already using it to build chemical models, test formation theories, and argue about what the interior might look like. Those models will generate predictions. Future observations will test those predictions. Some will survive, others will be thrown out. Slowly, the picture will sharpen. That process is how astronomy works. No single telescope solves the mystery. Each instrument hands the question forward to the next, a little better equipped. What makes PSR J23222650b unusual is that even the starting point, the 2025 spectrum, is already richer and stranger than the starting points for most characterized exoplanets. There is more to explain here. More unexpected chemistry, more structural strangeness, more competing theories. That richness is a gift to future researchers. It means the planet will remain scientifically productive for decades, even as better tools arrive to examine it. The atmosphere told scientists what molecules were present. Future work may reveal how those molecules got there. And one specific detail from the Webb data has scientists thinking about a type of chemistry that could, in principle, reshape understanding of how complex structures form in the universe. Carbon is the basis of life on Earth. Every protein in your body contains carbon, every strand of DNA, every cell membrane. Carbon's ability to bond with itself and with other elements in long, complex chains is what makes biological chemistry possible. In most planetary atmospheres, carbon is locked into simple molecules: carbon dioxide on Venus and Mars, methane in the outer planets, carbon monoxide in the gas clouds between stars. Simple 2 or 3 atom combinations that are stable and chemically quiet on PSR J23222650b. Carbon is doing something different. The molecular forms, Webb detected pure carbon chains of 2 and 3 atoms, are simpler than biological molecules, but more reactive than the stable forms carbon usually takes in planetary atmospheres. They are intermediate structures, sitting between simple molecules and complex organic chains. Those intermediate carbon structures matter because they are the building blocks from which more complex carbon chemistry can develop. In the outer layers of dying red giant stars, where carbon-2 and carbon-3 are also found, researchers believe those molecules eventually combine into larger carbon structures called polycyclic aromatic hydrocarbons, ringed carbon structures that are among the most common complex molecules in the universe. Those ringed structures have been found in meteorites, in interstellar clouds, and in the atmospheres of certain stars. On PSR J23222650b, is complex carbon chemistry actively developing? Could the conditions in this atmosphere allow those intermediate molecules to build upward into larger structures? Scientists have not answered this question yet. The atmosphere may be too hot and too radiation blasted for complex chains to survive long enough to accumulate. Or the conditions may be unusual enough that some carbon chemistry is progressing in ways that standard models do not predict. The relevance to life is indirect and speculative, but real. If complex carbon structures can form in the atmospheres of pulsar planets, then the universe may be producing the raw ingredients of complex chemistry in environments we had written off entirely. The question of where chemistry capable of leading toward biology can happen expands again. PSR J23222650b is not alive. There is no suggestion it is, but it is a carbon chemistry laboratory operating under conditions no Earth-based experiment can reproduce. What is happening in that atmosphere is real chemistry, running on a scale and under conditions that test the limits of what we know about how carbon behaves. Understanding it could tell us something about how carbon chemistry develops across the universe, in star-forming clouds, in the atmospheres of dying stars, and in whatever strange environments we have not yet catalogued. Every discovery about this planet's chemistry is also a discovery about the basic chemistry of the universe. And that chemistry, it turns out, is stranger and richer than our models had room for. The next question is whether the strangeness of this world is a rare exception or a sign of something broader hiding in our galaxy. Science works best with patterns. One observation is a curiosity. Two observations are a coincidence. Three or more start to look like a rule. PSRJ 23222-2650b is currently a curiosity. There is only one confirmed detection of an atmosphere around a pulsar planet with this kind of chemistry. One data point is enough to break a model, as it clearly has here. But one data point is not enough to build a new one. The history of astronomy suggests that unusual discoveries tend to multiply once scientists start looking harder. When the first hot Jupiter was confirmed in 1995, a gas giant sitting just 4 million miles from its star and completing an orbit in 4 days, it seemed like an impossible freak. Within a few years, hot Jupiters turned up everywhere. They are now one of the most studied categories of exoplanet. The universe produces them in large numbers, even though nothing in the original formation models predicted they could exist. Pulsar planets may follow a similar trajectory. The first pulsar planets were found in the early 1990s and stunned the field. Decades later, the total number of confirmed pulsar planets remains in the single digits. That low count may reflect actual rarity, or it may reflect how difficult pulsar planets are to find and how rarely dedicated searches have been conducted. If more pulsar planets are found, and more of them get atmospheric characterization from Webb or future telescopes, scientists will be able to compare them. Do they all show carbon-dominated atmospheres? Do some have conventional chemistry? Is the helium dominance common or specific to this one world? Do the formation histories cluster around one of the competing theories? Right now, those questions have no answers. The sample is too small. What PSR J2322-2650b has done is force researchers to take pulsar planets seriously as a class of object worth searching for. Before this world's atmospheric characterization, a pulsar planet was a rarity worth noting, but not a major focus of observational campaigns. After Webb's 2025 data, it is a priority. Searches are more likely to be funded and conducted when scientists have a reason to believe the results will be scientifically productive. This planet gave them that reason. If the searches find more pulsar planets, and if more of them turn out to have strange atmospheres, the field will have a pattern to explain. And patterns demand theories. Theories generate predictions. Predictions get tested. That chain is how science moves forward from one impossible-seeming object to a new understanding of how the universe works. The next step in that chain involves the most basic question of all. What does this planet tell us about the rules we use to understand every world we have ever studied? Every time a planet is discovered with unexpected chemistry or an orbit that defies expectation, scientists go back to their models. They ask, does this fit? Can we adjust the parameters and make the existing framework work, or do we need something fundamentally new? For PSRJ 232-22650b, the answer from the research team was clear. The existing models do not fit. Atmospheric models for exoplanets are built on a foundation of physics and chemistry developed over decades. Researchers know how molecules behave at high temperatures. They know how radiation interacts with atmospheric gases. They know how gravity holds atmospheres in place and how heat drives convection. Those principles are solid. The problem is that those solid principles predict a different atmosphere than the one Webb found. At the temperatures this planet likely experiences, with the mass it has, and sitting this close to a radiation source, standard chemistry calculations predict an atmosphere containing carbon dioxide, carbon monoxide, water vapor, and possibly methane. Some mix of those molecules is what every comparable model produces. Webb found almost none of those molecules. It found helium and pure carbon chains instead. When observations and models disagree, one of three things is true. The observations are wrong, the models are missing something, or the models are fundamentally wrong for this class of object. The observations from Webb have been reviewed and published. The instrument worked as designed. The spectral features are real. The first option is off the table. The second option, that the models are missing something, is the most common outcome in science. A missing ingredient, a process that was not accounted for, a chemical reaction pathway that researchers had not included. Scientists are working through this possibility, exploring whether pulsar radiation drives chemistry in ways not captured by current models, whether the planet's history includes events that reset its atmospheric composition, whether tidal heating produces conditions deep in the atmosphere that standard models ignore. The third option, that the models are fundamentally wrong for pulsar planet systems, is less comfortable, but also possible. If the formation history is genuinely unlike anything else in the catalogue, and if the ongoing environment is unlike anything else in the catalogue, then models calibrated on other kinds of planets may simply not apply. Researchers have not ruled out any of these explanations. The honest scientific position, as reflected in the published work, is that the atmosphere defies current explanation and that new theoretical work is needed. That admission is significant. Scientists are careful with those words. Saying a model fails is not a small thing. It is an invitation for the field to do better. And it is also, if you step back and look at the bigger picture, a sign that this planet is doing exactly what the best discoveries always do. It is pointing at the edge of knowledge, and just past that edge is where everything gets rebuilt. The history of science is full of moments where one observation rewrote the rules. One planet orbiting another star in a 4-day year, discovered in 1995, broke the idea that gas giants form only far from their stars. One observation of a supernova in a distant galaxy, published in 1998, broke the assumption that the expansion of the universe was slowing down and revealed that it was accelerating instead. One anomalous orbit of Mercury, just slightly off from what Newtonian gravity predicted, eventually led to general relativity. Single data points that do not fit the existing framework are the most productive objects in science. They are the places where the framework shows its seams. PSRJ 232222650b is one of those objects. It breaks the assumption that pulsar environments are atmospherically barren. It breaks the assumption that giant planet atmospheres follow predictable chemical patterns based on temperature and mass. It breaks the assumption that surviving near a millisecond pulsar for any significant time is possible for a body with a complex atmosphere. It raises serious questions about formation models that were not built to handle objects like this. Each of those broken assumptions is a research program. A team somewhere is now building a model that includes pulsar radiation effects on atmospheric chemistry. Another team is rerunning formation simulations, with pulsar environments at their center. Another is calculating how long different atmospheric compositions can survive given the radiation flux at 1 million miles from a millisecond pulsar. None of those research programs existed in their current form before 2025. One planet, one spectrum, dozens of new research directions. That is the productive chaos that a genuinely anomalous discovery creates. The scientific community does not retreat from confusion. It accelerates into it. The more questions a discovery raises, the more scientists it attracts, and the faster the field moves. PSR J 23222650b raised more questions per observation than almost any exoplanet in the current catalogue. It confirmed things that should not exist. It left gaps where expected signals should have been. It showed structure and chemistry that had no template. The researchers who published the 2025 Webb data described their own findings as difficult to explain. That phrase, in a scientific paper, is almost the highest compliment the field can give a discovery. It means the discovery is doing its job. It is being honest about the boundary of human knowledge. What lies just past that boundary is unclear. But the next chapter of this story is about the people who are working to find out, and why the work they are doing matters for every planet ever discovered, including the one you are sitting on right now. 750 light-years away, there is a planet with no oxygen in its sky, a world shaped like a lemon, circling a dead star in under 8 hours, wrapped in carbon clouds, blasted by radiation. Nothing about it sounds connected to life on Earth, and yet the scientists studying it are asking questions that feed directly into understanding Earth's own past. Earth has not always had the atmosphere it has today. 4 billion years ago, Earth had almost no free oxygen. The atmosphere was mostly nitrogen, carbon dioxide, and methane, a toxic mix by modern standards. Early microbial life existed in that environment and slowly, over hundreds of millions of years, transformed the atmosphere by releasing oxygen as a byproduct of photosynthesis. The Great Oxidation Event, roughly 2.5 billion years ago, is when oxygen first began accumulating in significant amounts. Before that event, Earth's atmosphere was chemically exotic by today's standards. An outside observer, looking at early Earth's spectrum through a telescope like Webb, would have found a world with strange chemistry. A world where oxygen was absent, where carbon compounds dominated in certain periods, where the surface and atmosphere were undergoing transformations we can trace in the rock record, but cannot fully model. PSR J2322-2650b is not early Earth. The comparison is imperfect in dozens of ways. But studying atmospheres with unusual carbon chemistry, with depleted oxygen, with extreme temperature and radiation conditions, helps scientists build better models of how atmospheres transform over time. Every exotic atmosphere Webb characterizes adds data to a database that Earth scientists and planetary scientists share. How does carbon behave at high temperatures? What conditions drive atmospheric escape? How do tidal forces alter internal chemistry? Those questions matter for Earth's history, for Mars's past, for Venus's evolution, and for every rocky world scientists hope to study in the future. PSR J2322-2650b is extreme enough that the lessons from it will not translate directly to Earth-like conditions. But the methods scientists develop to model it, the chemical frameworks they build to explain its spectrum, the radiation interaction models they construct to account for pulsar bombardment, all of those tools will eventually be applied to other worlds, including worlds that sit in habitable zones around stable stars. Understanding the exotic teaches us to better understand the familiar. That connection between the most extreme and the most familiar is also why the formation mystery at the center of this story matters so much. How this planet came to be tells us something about how all planets come to be. By chapter 15, this script had laid out the main competing theories for how PSR J2322-2650b formed. A planet born in the original stellar disk and surviving the supernova somehow. A planet formed from debris after the supernova. A planet formed far out and kicked inward by orbital chaos. Or a stellar remnant, the stripped core of a companion star, consumed by the pulsar's predecessor. None of those theories is confirmed. Scientists are still working through each one. But the formation mystery has a layer that has not been fully addressed yet. Whatever formed this planet did so in a way that produced an unusual chemical inventory. The atmospheric chemistry Webb found is not just strange for a planet in this orbit. It is strange for any planet of this mass, anywhere. That means the formation story has to explain two things: how the object ended up in this orbit, and how it ended up with an atmosphere dominated by helium and molecular carbon. A stellar remnant origin handles the second question somewhat better than the planet formation stories do. A stripped stellar core would have unusual elemental abundances by definition, because the stripping process removes the outer layers preferentially and leaves behind material from deeper inside the companion star. Deeper stellar layers have different ratios of carbon, helium, and other elements compared to the outer layers. A remnant of that stripping process could plausibly be enriched in helium and carbon relative to hydrogen, oxygen, and nitrogen. The stellar remnant story still struggles with the specific molecular forms Webb detected. Molecular carbon in the form of 2 and 3 atom chains is not a standard prediction even for stripped stellar remnants. Planet formation from supernova debris could also, in principle, produce unusual abundances, because supernova ejecta is chemically processed material from deep inside a massive star. Carbon, oxygen, and heavier elements produced by stellar nucleosynthesis get mixed and scattered. A planet forming from that material would inherit a non-standard chemical recipe. Neither pathway offers a clean, confirmed account of the specific atmosphere Webb measured. What researchers agree on is that the formation story, whatever it turns out to be, must explain both the orbit and the chemistry simultaneously. No current theory does both cleanly. That double constraint makes this planet unusually difficult to model and unusually rewarding to study. Each new piece of data narrows the range of possible explanations. The spectrum Webb collected in 2025 already eliminated many possibilities. Future observations will eliminate more. Eventually, what remains will be the truth. And that truth may be unlike anything in the current formation playbook. Everything about this planet comes back to the pulsar. The orbit is tight because the pulsar's gravity dominates at close range. The shape is a lemon because the pulsar's tidal forces stretch the planet. The temperature is extreme because the pulsar radiates intensely. The atmosphere's unusual composition may reflect years of pulsar radiation, stripping away hydrogen and lighter molecules. The cloud deck on the night side is driven by temperature contrasts that the pulsar creates. The westward winds are powered by the day-to-night temperature difference the pulsar maintains. A pulsar is not a passive object. It is one of the most energetic things in the known universe. A millisecond pulsar rotates hundreds of times per second. Each rotation, it sweeps its radiation beams across space. The magnetic field at its surface is roughly 1 trillion times stronger than Earth's magnetic field. The energy it pours into its surroundings is enormous and continuous. For a planet sitting 1 million miles from this object, every aspect of existence is shaped by that energy. The pulsar is not just a light source or a gravity source. It is an active agent in the chemistry, physics, and dynamics of everything around it. Scientists studying PSR J232222650b have to account for the pulsar, not just as a background condition, but as an active participant in the system's ongoing evolution. The planet's atmosphere is being driven by the pulsar. The planet's shape is maintained by the pulsar. The planet's winds and clouds and chemistry are all outputs of a system where the pulsar sits at the center, spinning, radiating, pulling, and transforming everything within reach. No model built for a planet around a quiet, sun-like star can simply be transplanted to this system. The pulsar changes every parameter. That is why the atmospheric composition that stumped scientists is not just a chemical puzzle. It is a puzzle about how a living, radiating, spinning neutron star interacts with a gas giant atmosphere over long timescales. Solving it requires a new kind of model, one that treats the pulsar as an active partner in the planet's chemistry rather than just a background gravity source. Building that model is the research program that PSR J232222650b has launched, and the planet sitting at the center of that program, stretched into a lemon shape, wrapped in carbon clouds, losing and possibly replenishing its atmosphere every orbit, is still out there right now, still circling, still changing. The pulsar has been spinning for a very long time. The planet has been circling for an unknown but long period, and the system will continue long after every current telescope goes dark. The question is whether, in the time we have to observe it, we can extract enough information to understand it. That requires going back to what Webb actually gave us, and what the limits of that gift are. Webb's atmospheric spectrum for PSR J232222650b J22650b is one of the most remarkable pieces of data collected in modern astronomy. It identified molecular fingerprints on a world circling a dead star, 750 light-years away, through years of planning, careful observation, and meticulous data analysis, and it is still incomplete. A transmission spectrum tells scientists which molecules absorb which wavelengths of light as the planet transits its host. It provides a chemical inventory of the upper atmosphere, the layers that the transiting light actually passes through. It does not tell scientists what is happening in the lower atmosphere, where pressure is higher and light cannot easily escape. It does not reveal the interior. It gives average abundances rather than precise maps. It captures a snapshot, not a history. For PSRJ 232-22650b, the incomplete picture means that several critical questions remain genuinely open. The interior structure is unknown, whether diamond formation is occurring, whether there is a rocky core, whether the planet is fluid throughout or has distinct layered regions. None of that is accessible from atmospheric spectroscopy. The long-term evolution of the atmosphere is unknown. Is the atmosphere shrinking over time, growing, holding steady? A single spectrum cannot answer that. Repeated observations over years would be needed to detect changes, and even then, the changes might be too slow for current instruments to measure reliably. The origin of the molecular carbon is unknown. Is it primordial, meaning the planet formed with a carbon-rich composition? Is it secondary, produced by ongoing chemistry driven by pulsar radiation? Is it a remnant of a previous atmospheric layer that was stripped away, leaving carbon behind as a concentrated residue? Each possibility points to a different formation and evolution history. The nightside cloud composition is not directly confirmed. The thick grey cloud deck is inferred from the blocking of spectral features. What those clouds are actually made of, whether soot-like carbon particles, some form of mineral aerosol, or something else entirely, cannot be determined from the existing data alone. These gaps are not failures. They are the next set of questions. Every answered question in science opens new unanswered ones, and the gaps in this spectrum are specific enough to guide exactly what future observations should target. Webb itself may be able to revisit this planet. Multiple observation windows, at different wavelengths, could fill in some of what the 2025 data missed. A different class of observation, phase curve mapping, which tracks the planet through its full orbit rather than just during transit, might reveal the temperature and chemistry distribution around the entire planet. The spectrum was a first look. What this planet actually is, at depth and over time, is still in the process of being discovered. Step back far enough and PSR J2322650b stops being a single strange world and starts being a statement about the universe. The universe is roughly 13.8 billion years old. Stars have been forming, living, and dying for nearly all of that time. Massive stars live fast and die in supernova explosions that leave behind neutron stars and pulsars. That process has been happening for billions of years, and it has produced an enormous number of pulsars scattered across every galaxy. If even a small fraction of those pulsars host planets, the number of pulsar planets in the universe is staggering. Most of those worlds would be invisible to us, too far away, around the wrong kind of star, unreachable by current technology. But they would exist, carbon-wrapped, radiation-blasted, lemon-shaped, racing through their short years in orbits no human instrument has yet touched. PSR J2322650b is one data point from that invisible population, a representative of a class of worlds whose size we cannot estimate because we have barely begun to count them. The discovery changes the scope of what the word planet means. For most of human history, planet meant the 8 worlds circling our Sunday. After 1995, it expanded to include thousands of worlds around other stars. After the pulsar planet discoveries of the 1990s, it stretched further to include worlds around dead stars. After 2025 and Webb spectrum, it now includes worlds whose atmospheres contain chemistry we cannot explain, in environments we once considered lethal to any kind of organized molecular complexity. Each expansion of the definition has been driven by data. Each time scientists thought they knew the limits of where planets could be and what they could look like, a new discovery pushed those limits outward. The current state of knowledge is that we do not know where the limits are. We know they are farther than we thought. We know there are environments we classified as barren that are hosting active, complex, chemically rich worlds. We know our models have gaps large enough to contain an entire atmospheric chemistry we had not predicted. That is a sobering realization, sobering and exciting in equal measure, because a universe larger and stranger than our models describe is a universe with more possibilities than we have accounted for. PSR J2322-2650b is one node in a map of those possibilities, a map that is still mostly blank. The blank parts of that map are where the most interesting discoveries are hiding, and finding them requires building on everything this planet has taught us, while accepting that the most important discoveries about it may still be ahead. Scientists are comfortable with uncertainty in a way that takes most people time to appreciate. An unknown is not a failure. An unknown is a coordinate. It marks a place on the map where work still needs to happen. For PSR J2322-2650b, the list of confirmed unknowns is long and specific. The origin of the planet is unresolved. Scientists cannot confirm whether this world formed from a protoplanetary disk, from supernova debris, from material captured after the pulsar formed, or whether it is a remnant of a consumed stellar companion. The exact radius of the planet is not securely established from two independent sources. The atmospheric characterization gives a strong chemical picture, but the physical size remains uncertain. The precise global temperature is unresolved. Different measurements and different models give different values, and no single confirmed temperature describes this world. The composition of the nightside cloud deck is unknown. The thick grey layer blocks the spectral signal from below and has not been chemically identified from the available data. The full extent of atmospheric escape is unknown. Scientists know hydrogen appears depleted. How much total mass the planet has lost over its lifetime, and how fast it is currently losing material, has not been measured. The interior structure is unknown. Whether diamond formation is occurring, whether a rocky or metallic core exists, whether the interior is differentiated into distinct layers. None of this is accessible from atmospheric spectroscopy. Whether the atmosphere is stable, growing, or shrinking over time is unknown. A single spectrum provides no baseline for comparison. Long-term monitoring would be required to detect trends. Why oxygen and nitrogen are so depleted, beyond the general hypothesis of radiation stripping, is not confirmed. The specific mechanism or combination of mechanisms that removed two common elements from this atmosphere remains without a satisfying explanation. The exact distance from Earth is in dispute between the parallax-based figure of roughly 750 light-years and later reports citing over 2,000 light-years. That list is not a list of failures. Every item on it is a target, a specific question that a specific observation or a specific model could answer. Scientists are working on all of them. Progress will come. Some items will be resolved by future Webb observations. Others will require telescopes not yet built. What the list shows is that PSR J23222650b is a scientifically productive object. A world with this many open questions is a world that will keep generating research, attracting attention, and producing new discoveries for years. When the Webb team published their findings on PSR J23222650b in 2025, the response from the wider scientific community was immediate. Papers began citing the results within weeks. Research groups that had been focused on other classes of exoplanets started requesting telescope time to look at pulsar systems. Formation theorists went back to their simulations. That kind of rapid response is unusual. It happens when a discovery is genuinely surprising, when the data is clean enough to trust, and when the implications are broad enough to affect multiple subfields at once. PSR J23222650b hit all 3 marks. The surprise was total. No existing model predicted a helium and molecular carbon atmosphere on a pulsar planet. The closest analog, atmospheres around dying red giant stars, exists in a completely different context and does not match the full picture Webb provided. Researchers went into this observation with expectations based on what they knew about hot Jupiter chemistry, and what they got was something from an entirely different category. The data quality was high enough to publish with confidence. The spectral features were clear. The molecular identifications were secure. The confirmation that this world's chemistry defies current models was not an artifact of noise or instrument error, and the implications spread across planetary formation theory, atmospheric chemistry, radiation, physics, and the basic question of where in the universe complex chemistry can persist. Rewriting a playbook does not happen in a single paper. It happens over years of follow-up work, failed models, revised models, new observations, and eventual convergence on a better understanding. PSR J23222650b started that process. The playbook being rewritten is the one scientists use to understand what a planet can be, what environments a complex atmosphere can survive, what chemical compositions are possible for a gas giant, what formation pathways the universe can produce. Each page of the old playbook that gets revised makes the new version more accurate, and a more accurate playbook means better predictions for the next discovery, and the one after that. This planet did not just raise questions, it raised better questions. Questions specific enough to guide the next decade of atmospheric research on pulsar systems. And now, with all of that in view, it is worth asking the question that started this entire story, from a place of full understanding rather than initial surprise. The title of this story is a scientific statement, not a dramatic one. By the rules in place before 2025, PSR J232222650b should not exist in its current form. Each rule it breaks was established from real data and real physics. Each violation is specific. Giant planets are not expected to survive in tight orbits around millisecond pulsars because the formation pathways that produce giant planets require conditions incompatible with pulsar environments. Giant planets that somehow do survive near pulsars are not expected to retain complex atmospheres because pulsar radiation at close range should strip lighter atmospheric components over cosmological timescales. Giant planet atmospheres, at the temperatures this world likely experiences, are not expected to show molecular carbon as a dominant species, because standard chemistry models predict carbon would bond with oxygen and hydrogen into more common molecules. The absence of oxygen and nitrogen in an atmosphere of this mass and temperature range is not predicted by any standard model of giant planet chemistry or atmospheric evolution. Every one of those expectations has observational and theoretical backing. They were not arbitrary assumptions. They were built from hundreds of observations of other worlds and decades of theoretical work. PSR J23222650b violates all 4 of them simultaneously. That is why scientists used the language they used. Defies explanation, impossible to account for with known formation mechanisms. Atmosphere, unlike anything in the catalogue. When one discovery violates 4 separate established expectations at once, the discovery is telling scientists something important. Either 4 separate things went wrong in the models simultaneously, an unlikely scenario, or something deeper is missing from the framework itself. A process, a chemical pathway, a formation mechanism, or an environmental effect that nobody had yet accounted for. Science responds to that kind of signal by going back to first principles. What do we actually know as opposed to what have we assumed? Where did the assumptions come from? And are those sources still valid when applied to pulsar systems? What would the models need to include to produce the atmosphere Webb measured? Those questions are being asked right now. The planet is still out there, still circling, still wrapped in its carbon and helium sky. The pulsar is still spinning. The lemon shape is still held in place by tidal forces. The soot-like clouds are still condensing on the night side. The westward winds are still blowing, and far closer than 750 light-years away, in universities and observatories and research offices, scientists are still working out why it should not be there, and what its existence means for everything they thought they knew. One planet, 750 light-years away, shaped like a lemon, wrapped in a carbon sky, racing through its short years in silence and radiation. It seems like an isolated story, a strange object in a far corner of the galaxy, interesting to specialists but disconnected from anything that touches daily life. The last lesson of PSR J23222650b is that this framing is wrong. Every time science has discovered a world that should not exist by the rules of the day, the rules got better. Hot Jupiters forced researchers to rewrite planet migration theory. Super-Earths forced a new category of planet that our solar system does not have. Ocean worlds hidden under ice, like Europa, forced a new definition of where liquid water can persist. Each impossible world made the model of the universe more accurate. PSR J23222650b is doing the same thing. Its carbon atmosphere is not a curiosity sitting outside the boundary of scientific relevance. It is a new data point that will eventually be incorporated into a better theory of how planets form, how atmospheres evolve, and how chemistry persists in extreme environments. That better theory will then be applied to every other planet scientists study, including rocky worlds that could potentially host life. The tools refined to read this planet's spectrum will read other planets. The radiation models built to explain what pulsar bombardment does to an atmosphere will be applied to atmospheres around white dwarfs, around X-ray binaries, around any star with unusual energy output. The formation theories tested against this world's existence will clarify which pathways the universe actually uses to build planets in difficult environments. One lemon-shaped planet is training the instruments, the models, and the scientists who will eventually find things far closer to home, scientifically speaking. Smaller planets, atmospheres with oxygen, worlds where the question of life becomes real rather than theoretical. The universe is not organized around human categories. It does not sort planets into the boxes we build. It produces objects that fit our expectations, and objects that break them, and the objects that break them are the most important ones, because they force us to build better boxes. PSR J23222650b broke several boxes at once. The research it launched will take years to conclude. The questions it raised will take a generation of astronomers to answer. The better models it will eventually produce will be used by scientists who have not yet started their careers. That is the deepest truth this planet offers. Science is a project that spans lifetimes. Each discovery hands something forward. Each impossible world that gets explained makes the next impossible world slightly easier to understand. 750 light-years away, a lemon-shaped planet circles a dead star in under 8 hours, wrapped in carbon clouds and westward winds, shaped by forces that should have destroyed it, holding an atmosphere that should not survive. It has been there for a very long time. It will be there for a long time after we figure it out. And somewhere in that gap, between what we know now and what we will eventually understand, the next discovery is already waiting.